Okay, welcome to our second example on mass density. So if you remember from kind of the last few videos, we've been talking about this special property that we can use to distinguish different types of substances, right? We can distinguish milk from water, from soda, from a rock, from any other substance, right? And mass density is really just the mass per unit volume of that substance. So in this example, let's say you baked some brownies in a pan, right? And then you broke those brownies into 3 different sections, and each section is going to be a different size, right? A different volume. So the question is, order each piece's mass density from smallest to largest, right? So let's draw a diagram here to really understand this problem. So bear with me. Let's say this is your tray of brownies, right? And you took these brownies and you split it maybe down the middle, and then maybe you just had this uneven piece here. So I'll call this piece A, I'll call this piece B, and I'll call this piece C. So remember, the question is asking for us to rank each of these 3 pieces, their mass densities from smallest to largest. So remember, mass density, which we represent using the Greek letter rho, is equal to mass of that substance divided by the volume that it takes up, right? So if we looked at piece A, and I drew piece A here, so this is piece A, I could say that the mass density of A is equal to, well, the mass of A divided by the volume of A, right? And if I did something similar to part B, I could draw this right here. This is B, and the mass density of B is equal to, well, the mass of B divided by the volume of B, right? And then finally, we have this tiny piece here that we have C. So the mass density of C is really just the mass of C divided by the volume of C. Right, so each of these pieces has their own mass densities because they're broken up into 3 separate pieces. And remember, the mass density is what we use to differentiate different substances. Not necessarily these 3 pieces, but what these 3 pieces are made out of, right? Each of these 3 pieces are from the same tray of brownies, so we can safely assume that A is brownies, B is brownies, and C is brownies. But the question asks, order each piece's mass density from smallest to largest. And just by looking at how we cut these pieces, you might say that, well, since mass C is smaller, that's probably going to have the lowest mass density. And if part B is the biggest piece, then that might have the highest mass density. But remember, this relationship between mass and volume, which is what we call mass density, is the ratio of mass per unit volume. So mass per unit volume, right? And what do we know about unit volume? Well, if we're measuring length in, let's say, centimeters, a unit volume would be centimeters cubed, right? And we're really looking at how much mass is there per 1 cubic centimeter, right? Or if you measured in meters, this would be 1 cubic meter, right? Or inches would be 1 inches cubed, right? 1 cubic inches. But since brownies are pretty small, I'm just going to go ahead and use the unit of centimeters just for this example, right? So what the question is asking is not how big each piece is or how much mass there is in each piece, but rather how much mass is there per unit volume in each of these pieces. And then once we figure that out, we can calculate the mass densities, right? So if I looked at piece A and I took 1 small cube out of this portion of the brownie, right? And each side of this cube was 1 centimeter, and I did the same thing for piece B, right? This is 1 cubic centimeters of piece B, and then I did the same thing for C, right? So in each of these 3 pieces, we're measuring 1 cubic centimeter of the brownies for each of these pieces, right? So I have piece A, piece B, piece C, right? So this is A, B, and C. 1 cubic centimeter of brownie from each of these 3 sections. Now, if we look at each piece of brownie here, well, if we measured this on a scale and each piece was 1 cubic centimeter, you could safely assume that each piece is going to weigh the same. In other words, in 1 cubic centimeter of piece A, this little cubic unit volume in piece A is going to have the same mass as this piece in piece B as this piece in piece C. So the masses are going to be the same because we're measuring just 1 cubic centimeter in each of these 3 sub-pieces, right? Or in other words, what we're really seeing here is that the mass density of A is equal to the mass density of B is equal to the mass density of C. Because it really doesn't matter how much volume each one of these 3 pieces takes up, right? We're simply looking at, for each piece, how much mass is there contained in 1 unit of volume in each of the 3 pieces. And we know those are going to be the same. And that makes sense, right? If we looked at each one of these 3 pieces, well, density A, the mass density of A, is really the mass of A, this piece A, over the volume of A, right? So if we increase the mass, well, that means we're going to increase the volume, right? If the mass density is the same. However, if we kept this same volume in purple, but we increase the mass, then there would be more substance per unit of volume of A. And that would make row A not equal to row B, not equal to row C. So remember, whenever we're looking at this concept of mass density, we're looking at the ratio of mass to volume, and not necessarily the mass individually or the volume individually, right? Now, if row A or row B or row C was different from the other values, we could probably assume that, maybe piece B was not a brownie. But in the case of this example, this is one uniform piece of brownie, and it doesn't matter how many sections we cut this up in, because all 3 pieces are the same type of brownie, they're going to have the same mass density per unit of volume, right? They're going to have the same mass per unit of volume. So really, to answer this question of ranking them from smallest to largest, it's actually a trick question, right? We discovered that all the densities in each 3 of these pieces are the same because they're really from the same substance. And ranking them isn't dependent on strictly mass or volume, but rather the ratio of mass to volume in each one of these 3 pieces.